Welcome to Sleepy Astronomy. I'm so grateful you have joined me tonight. Let your thoughts drift freely as your body grows heavier with rest. Above us lies a soft band of starlight, faint yet familiar, a reminder that we are part of something vast. This is the Milky Way, our galaxy, a sprawling collection of stars and dust that curves gracefully across the dark, like a quiet, cosmic tide. The Milky Way is our home in the universe, a vast spiral galaxy composed of hundreds of billions of stars, countless planets, and mysterious clouds of gas and dust. It stretches across more than 100,000 light-years from end to end. When we look up into a clear night sky and see a faint, glowing band of light, we are gazing along the plane of this immense structure. Ancient cultures saw it as the path of spirits or the spilled milk of the gods. Today, science reveals a deeper story, one told in hydrogen atoms, star clusters, and gravitational fields. The Milky Way belongs to a small group of galaxies known as the Local Group. There are just a few dozen members, most of them smaller dwarf galaxies, dominated by three large spirals, our own, Andromeda, and Triangulum. These galaxies share a gravitational bond, orbiting one another slowly over billions of years. Our galaxy is not isolated, but part of a larger cosmic family. Viewed from a distance, the Milky Way would resemble a fattened disk of stars with a central bulge and graceful spiral arms that curl outwards. These arms are not fixed structures, but patterns shaped by density waves, slow-moving swells where gas and dust are compressed and stars are born. The entire galaxy rotates slowly, completing one full turn every few 100 million years. Stars near the core move faster, while those farther out drift more slowly, tracing stellar paths shaped by gravity and dark matter. Our solar system lies in one of these spiral arms, called the Orion Arm, about 27,000 light-years from the galactic center. From this vantage point, the heart of the galaxy remains hidden behind dense clouds of interstellar dust. Yet radio and infrared observations allow us to peer through the obscuring veil, revealing the tightly packed sphere of stars that makes up the galactic bulge. Deep within it lies a supermassive black hole, quiet and invisible, but influencing the surrounding stars with its immense gravitational pull. Much of the Milky Way's mass is unseen. Ordinary matter, every star, planet, and cloud, makes up only a fraction of the whole. The rest lies in an elusive form we call dark matter. Though invisible, it exerts a gravitational effect, holding the galaxy together, preventing the fast-moving stars at its outer edge from flying away. Without it, the Milky Way, as we know it, would not exist. A faint, roughly spherical halo surrounds the galaxy, extending far beyond the visible stars. This halo harbors globular clusters, dense gatherings of ancient stars, along with dark matter and streams of stars torn from smaller galaxies that ventured too close. These remnants tell a story of cosmic cannibalism. Over billions of years, the Milky Way has grown by drawing in smaller neighbors, absorbing their stars, and reshaping their streams into the fabric of its own disk. Despite its size and age, the Milky Way remains active. Stars are still forming in its spiral arms, particularly in dense clouds of gas known as molecular clouds. These regions are nurseries of light and heat, giving birth to new suns and planetary systems that will orbit them for billions of years. The Milky Way is more than a collection of stars and dust. It is a dynamic structure with layers of complexity and scale that challenge the imagination. It forms the backdrop to our solar system's journey across the cosmos, a vast and glittering canvas painted across time and space. Living within a galaxy like this is both humbling and inspiring. It reminds us that we are part of something far greater than ourselves. From beneath this spiral roof, we wonder, we explore, and we reach outward, seeking to understand the structure and history of the universe. The Milky Way is the storybook from which we read the cosmic past. It is the wellspring of stars, the cradle of planetary systems, and the home of every human being who has ever lived. From our vantage point within the great wheel of the Milky Way, we peer out into a colossal structure, spun from stars, gas, dust, and dark matter that extends across more than 100,000 light-years. Among all its grandeur, the galaxy presents a form that is at once majestic and well-ordered, a spiral that winds through space with elegance and power. The Milky Way is classified as a barred spiral galaxy. This shape is defined by several remarkable structures. The most noticeable are the sweeping spiral arms. These are not fixed streams of stars, but rather regions of higher density, where material has become concentrated by waves of gravity moving through the galactic disk. Within these arms, stars are born in vast numbers. The arms blaze with blue-white light from hot, massive stars, stars that live fast and die young. The spiral arms also contain molecular clouds, the cold nurseries from which new stars emerge. We can identify several arms from our position inside the galaxy, notably the Perseus arm and the Scutum, Centaurus arm. The Sun itself lies near the edge of a minor arm, known as the Orion Spur. Turning inward, we arrive at the central bulge. This is a densely packed, spheroidal region sitting at the heart of the galaxy. It contains ancient stars, some of them merely as old as the universe itself. These stars have low metallicity, meaning they formed very early, before successive generations of supernovae seeded the cosmos with heavier elements. The bulge emits a warm, reddish glow, the signature of stars that have reached the later stages of their lives. Threaded through the central bulge is the bar, a bar-shaped core of stars and gas, stretching across the middle of the galaxy, about 27,000 light-years long. This bar plays a crucial role in the Milky Way's dynamics. It funnels matter inward, feeding the supermassive black hole at the very center of the galaxy, and it channels gas from the disk into regions where new stars can fall. Recent surveys using infrared telescopes have revealed the full dimensions of the bar, previously difficult to detect because of dust that blocks visible light. Encasing the disk and bulge is the galactic halo. This vast, faint sphere extends far beyond the visible edge of the galaxy. It is primarily composed of dark matter, but we also find globular clusters, tightly bound groups of ancient stars orbiting the galaxy in elliptical paths. These clusters are some of the oldest objects known, and they orbit within the halo like satellites. The halo contains a sparse population of stars, many of which belong to population 2, low in metals and high in age. The disk itself is thin and flat, turning slowly like a vinyl record floating in space. It includes not only the spiral arms, but also interstellar gas, dust, and billions of stars. This is where most of the galactic activity occurs. Here, the complex life cycle of stars unfolds. Birth in molecular clouds, brilliant main sequence lives, and spectacular deaths. The disk is also where planetary systems form. including the one we call home. Together, these parts form a gravitationally bound whole, shaped over billions of years by the invisible pull of matter. Each component interacts with the others, driving motion, triggering star formation, and anchoring the history of the galaxy. Though it spans 100,000 light-years, the Milky Way is more than just a structure of stars. It is a living system, evolving over time, responding to the forces around and within it. And as we chart the spiral arms, model the bar, and watch the stars journey through the halo, we uncover not only the structure of our galaxy, but the deeper narrative of cosmic time. The past and the future, written in stars and dust, carried within the great wheel that slowly turns above us. Scattered through the spiral arms and nestled within the bulge and halo, lie the stars, billions upon billions of them. They span every stage of life, from newborn flashes of nuclear ignition to fading remnants of once mighty suns. Their differences tell a story of time and formation, of change and fusion, and of the galaxy's evolving history. Stars come in many sizes and colors. Some, like our Sun, are yellow stars of medium mass. Others are small and cool, red dwarfs that shine faintly and live for trillions of years. The largest are the blue giants, burning hot and fast, living for only millions of years before ending in violent supernovae. There are white dwarfs, the dense embers left by smaller stars, and neutron stars, crushed cores of massive stellar explosions. Scattered even farther are the elusive black holes, invisible yet powerful. Astronomers classify stars into groups, not just by type, but by their age and chemical makeup. We see this in the concept of stellar populations. Population I stars, like the Sun, are found in the spiral arms. They are relatively young and contain higher concentrations of elements heavier than hydrogen and helium, what astronomers call metals. These metals are forged in the hearts of older stars and scattered by supernovae. Every new generation is enriched by those that came before. Population II stars are older. They formed when the galaxy was young, a time when heavier elements were rare. These stars reside mostly in the central bulge and the halo, orbiting the galaxy in long, tilted paths, far from the flat disk. Their lower metallicity tells us they formed early, before the galaxy had cycled through many waves of star birth and death. And beyond them, theoretical still, lie population V stars. These would have been the first stars ever to ignite, born from pure hydrogen and helium shortly after the Big Bang. None have ever been observed directly. If they ever existed, they lived brief and brilliant lives, synthesizing the first heavier elements and seeding the universe with the building blocks for everything to come. Their legacy is etched into the chemistry of the cosmos. Star formation begins within dark molecular clouds, where gas and dust gather in cold silence. Over time, gravity pulls these clouds into denser regions called protostars. As the pressure builds at the core, the temperature rises. When it crosses 10 million degrees, nuclear fusion ignites. A star is born, burning hydrogen into helium. Some of these stellar nurseries span hundreds of light years, overflowing with infant stars still cloaked in the dust from which they formed. These star-forming regions are not evenly spread throughout the galaxy. Most are found along the spiral arms. There, density waves compress the gas as they pass, triggering collapses and new births. The central bulge, though densely packed with older stars, has less raw material. Star formation is rare there. The halo, wide and sparse, is home mostly to globular clusters, ancient spherical collections of population II stars, orbiting like satellites around the galactic center. The distribution of stars across the Milky Way reveals its structure and its past. The youngest stars, with their glowing nebulae and restless clusters, illuminate the flat galactic disk. Older stars drift through the bulge and drift even farther in the vast halo. This layering reflects the galaxy's history, from a time of chaotic mergers and rapid formation to the more settled spiral it has become. Each star is a memory. Its light travels years or thousands of years to reach us, carrying stories of where and when it was born. And together, the stars tell the broader story of our galaxy itself, not as a frozen picture, but as a living, evolving system. At the heart of the Milky Way, hidden behind veils of interstellar dust, lies one of the most enigmatic objects in the universe. It is a region of gravity so intense that nothing, not even light, can escape its grasp. Astronomers call it Sagittarius A star. It is a supermassive black hole, and it sits in the exact center of our galaxy. For millions of years, it has governed the motions of stars in the inner galactic core, silently shaping the dynamics of the Milky Way. The discovery of Sagittarius A star began not with a photograph, but with the subtle clues left behind by the stars themselves. In the late 20th century, radio telescopes pointed at the constellation Sagittarius began detecting an unusually strong and compact radio source. Further observations, stretched over decades, tracked the movement of stars near the galactic center. These stars, some traveling at thousands of kilometers per second, followed curved and accelerated paths, clear signatures of an immense mass bending the geometry of space. One star in particular, known as S2, revealed the truth. Every 16 years, it swings in a wide arc around a single invisible point and then slingshots past it at dizzying speed. The only possible explanation is a central mass equivalent to more than 4 million times that of the Sun, packed into a region no larger than our solar system. That object, Sagittarius A star, can be nothing other than a black hole. Its mass and influence are staggering. Within the central few hundred light-years of the Milky Way, Sagittarius A star dominates gravitational interactions. Stars in that region move in complex orbits, their motions dictated by unseen forces. These stellar dances allow astronomers to map the invisible, much like tracking the wind by watching the sway of leaves. It's through such indirect evidence that we understand the black hole, not as an isolated feature, but as a central engine driving the galactic core. Sagittarius A star is not presently active in the way that black holes and some other galaxies are. In certain places, supermassive black holes consume vast quantities of matter, creating energetic jets that blaze across space. But Sagittarius A star is relatively quiet. Currently, it accretes only tiny amounts of gas and dust. Even so, it occasionally brightens in brief flashes of X-rays, like restless stirrings in its sleep. These moments allow us fleeting glimpses into the processes happening near the event horizon, where matter is pulled to destruction. Though mostly dormant, the black hole remains essential to the structure of the galaxy. Its immense gravity provides a stabilizing anchor for the entire Milky Way. In the central bulge around it, tens of millions of stars orbit, locked in celestial patterns that have persisted for eons. Without such a massive object at the center, the galactic dynamics would be far less orderly. The presence of Sagittarius A star suggests something more profound as well. We now believe that most large galaxies harbor supermassive black holes at their centers. These giants may have formed early in the universe, growing through mergers or by devouring surrounding matter. In time, they seem to co-evolve with their host galaxies. The mass of the central black hole correlates strongly with the mass of a galaxy's bulge, hinting at a deep connection between a galaxy's formation and its central darkness. Perhaps it is no coincidence that the Milky Way, with its trillion stars and rich spiral arms, finds balance through a single, invisible object holding court in the center. In the contrast between its silence and its power lies a deep truth about the universe, that the things which shape us most profoundly are often hidden from sight. And so, Sagittarius A star remains, locked in the shadows, a gravitational anchor and a reminder. It is a beacon of absence that pulls stars into their orbits, a singular point where knowledge and mystery meet. Everything we see in the night sky spirals in relation to it. It is the dark heart of our galaxy. Drifting between the stars of the Milky Way lies a vast and delicate structure, unseen by the naked eye, but essential to the life of the galaxy. This is the interstellar medium. It is not empty space, but rather a thin mix of gas and dust, stretching out across light years between stars. Though diffuse, it holds the seeds of suns and the potential for new worlds. Most of the interstellar medium is hydrogen, by far the most abundant element in the universe. It exists in different forms as single atoms in the warm regions of space, or bound together as molecular hydrogen in colder, darker areas. Alongside the hydrogen are traces of helium, carbon, oxygen, and other heavier elements, all forged long ago in stellar furnaces and scattered through supernovae. Floating within this gas are tiny grains of dust, microscopic particles of silicates, carbon compounds, and ices. These grains make up only about 1% of the interstellar medium by mass, but they have a profound effect. They block and scatter light, creating the dark bands that stretch across the Milky Way. In certain regions, the gas and dust come together in more concentrated pockets, known as molecular clouds. These are the cradles of star formation, chilled to temperatures just above absolute zero. Protected from the harsh radiation of starlight, the hydrogen becomes molecular, and gravity begins its quiet work. Over time, parts of the cloud contract under their own weight. As they collapse, they fragment. And inside those fragments, pressure and temperature gradually rise. When the core becomes hot enough, nuclear fusion ignites, and a new star is born. From a distance, these regions of star birth shine with a gentle luminosity. We call them nebulae. Some are sculpted by the winds of young, massive stars that have recently emerged from the cloud that created them. Others glow with the light of nearby stars, ionizing the surrounding gas, creating the brilliant colors we see in long-exposure photographs. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of the closest and best-studied star-forming regions. Inside it, entire systems are taking shape. Stars, planets, and perhaps the conditions needed for life. The interstellar medium does not just make stars, it is also shaped by them. Supernova explosions blast heavy elements back out into space, stirring the surrounding material and enriching it. Stellar winds from massive stars carve out great cavities, called bubbles, in the gas. These processes feed energy into the medium, heating and dispersing the gas, and then compressing it again. It is a cycle of creation and destruction. The death of one star may help to trigger the birth of another. Altogether, the interstellar medium operates as a kind of circulatory system for the galaxy. It carries matter and energy between stars. It fosters the birth of solar systems, seeds the environment with complex molecules, and records the history of past generations of stars. The patterns of gas and dust reveal the structure of the Milky Way itself, outlining its spiral arms and the places where new stars are emerging even now. Though largely invisible to our eyes, the interstellar medium surrounds us. Light from distant stars filters through it before reaching Earth. Radio telescopes detect the unique fingerprint of cold hydrogen atoms drifting across space. Infrared observatories pierce the opaque veils of dust to glimpse stars still in their infancy. Piece by piece, we build a picture of a galaxy that is not a static collection of stars, but a dynamic, breathing system in which matter flows, evolves, and transforms. In these quiet oceans between the stars, the past and the future come together. Dust from long-dead suns mixes with gas still untouched by fusion. Together, they form the foundations of yet unborn stars, reconciling stillness with movement, silence with creation. This is the interstellar medium, not empty space, but a living bridge between stars. As we gaze out into the starry sky on a clear night, we're peering into the arms of a grand spiral galaxy, our home, the Milky Way. It stretches some 100,000 light-years across, its stars and gas forming a magnificent rotating disk. But the motion of this galactic giant is far from simple. It is not a solid wheel turning in unison, but a dynamic, fluid system governed by gravity and the invisible influence of things we cannot yet see. At the heart of our understanding lies the galactic rotation curve, a graph of how fast stars and gas orbit the center of the Milky Way at different distances. Intuitively, one might expect that stars farther from the center would move more slowly, just as planets further from the Sun have longer orbital periods. In the inner regions, this seems to hold. Stars closer to the core revolve more swiftly, influenced by the gravitational pull of the densely packed mass within the central bulge. But beyond a certain distance, around 20,000 light-years from the galactic center, the expectations unravel. Rather than declining, the rotational speed levels off. Stars in the outer reaches are moving much faster than gravity from visible matter can explain. The curve is flat, and this discrepancy has deep implications. This is where the mystery of dark matter comes into sharp focus. The visible stars, gas, and dust cannot account for the speeds observed. There must be something else, something massive, yet unseen, enveloping the galaxy in a vast spherical halo. This dark matter does not emit or absorb light. We cannot detect it directly, but its gravitational pull holds stars in place and shapes the motions of the Milky Way at the largest scales. It turns out that most of the galaxy's mass, perhaps as much as 85%, resides in this unseen form. The stars we see are merely the bright frosting on a much larger cosmic structure. This discovery reshaped astrophysics, revealing that we live in a universe filled with matter we do not yet understand. The Milky Way does not rotate as a rigid body. Its disk displays what is known as differential rotation. Stars at different radii orbit the center at different speeds. This twist causes the spiral arms to wind and stretch, and contributes to the beautiful structure we see today. Even our Sun participates in this cosmic motion. It dwells in what astronomers call the Orion Arm, a small spur located between two of the galaxy's major arms, Sagittarius and Perseus. The Sun orbits the center of the Milky Way at an average speed of about 220 kilometers per second. It takes roughly 225 million years to complete a single galactic orbit. This journey is known as a cosmic year. During that time, entire eras come and go on Earth. But last time the Sun was in roughly the same position. The dinosaurs were just beginning to walk the land. Life has evolved while the solar system cruised leisurely around a calm galactic core. And at the center of this vast turning wheel is Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. The Milky Way moves in ways both elegant and strange. It rotates not like a clock, but like a living system, governed by gravity, shaped by mystery. And through it all, the planets, the stars, and indeed our own pale blue world, continue their silent arc across the galaxy's immense and unseen design. Beyond the graceful spiral arms and glowing heart of the Milky Way, there hangs a quiet, cosmic entourage. The Milky Way is not alone. It is surrounded by a collection of smaller galaxies called satellites. Some are tiny whispers of starlight, barely measurable in the black sea of space. Others, like the Magellanic Clouds, are bright enough to be seen with the naked eye from the southern hemisphere. These companions dance in the galaxy's gravitational grip, orbiting slowly, interacting, and sometimes falling inward in silent collision. The two most prominent satellite galaxies are the large and small Magellanic Clouds. They are irregular in shape, unlike the elegant spiral of the Milky Way. The Large Magellanic Cloud, or LMC, is the more massive of the two. At about 160,000 light-years away, it spans roughly 14,000 light-years, home to star-forming regions such as the Tarantula Nebula. It pulses with newborn stars and glowing gas. The small Magellanic Cloud, slightly farther away, is less massive and more distorted, torn by the Milky Way's tides. These two galaxies themselves are bound in a loose orbit around each other, and together they orbit the Milky Way in a complex, looping path. But the Magellanic Clouds are only part of the story. Astronomers have discovered more than 50 satellite galaxies orbiting the Milky Way. Most are dwarf spheroidal galaxies, small and faint, made up of old stars and very little gas. They range in size from a few hundred light-years across to a few thousand, and many contain only a few million stars. These dwarfs are the fossils of earlier cosmic times. They remind us of the early universe, where small structures formed first and merged into larger galaxies. Among the most studied of these satellites are the Sagittarius dwarf spheroidal galaxy and the Fornax dwarf galaxy. The Sagittarius dwarf, stretched and disrupted by the Milky Way's gravity, has been falling into our galaxy for billions of years. It trails stars behind it in long streams, like a comet across the sky. Each time it passes through the Milky Way's disk, it stirs the stars, reshapes the motion of gas, and leaves behind evidence of its journey, written in the gravitational ripples. The gravitational interactions between the Milky Way and its companions are subtle, yet far-reaching. As these small galaxies fall inward, they lose stars, stripped away by tidal forces. Gas is pooled into elongated streams. Some of these flows feed future star formation. Others form vast arcs that encircle the galaxy. The Magellanic Stream, a ribbon of hydrogen gas extending over 200 degrees across the sky, was torn from the Magellanic Clouds. It is now falling slowly toward the Milky Way, a river of raw material traveling through space. These interactions are not one-sided. The presence of satellites and their constant pull can warp the Milky Way. The outer disk undulates like a ripple on water. Some regions of the galaxy's halo contain ancient stars that originally belonged to merging companions. Over billions of years, these mergers compound. Each satellite absorbed adds to the mass of the galaxy, helping shape the spiral structure we call home. Cosmological simulations suggest that galaxies like ours grow through such interactions. The Standard Model of Cosmology predicts a universe filled with dark matter, in which galaxies form at the centers of dark matter halos. Smaller halos, the gravitational homes of dwarf galaxies, merge over time, forming larger and more complex structures. The Milky Way's companions today are the survivors, the remnants of earlier epochs in a long, unfinished assembly. In the night sky, the Magellanic Clouds appear fixed, but their journey is inexorable. The Large Magellanic Cloud is on a decaying orbit. It may one day collide with the Milky Way in a slow shell-building embrace. Stars will scatter like sparks in a breeze. These future mergers will not destroy the galaxy, but they will transform it. They will trigger star formation, redistribute mass, and alter galactic motion. On the grand stage of the cosmos, even galaxies are shaped not in isolation, but in relationship. The Milky Way satellites are not distant strangers. They are family, joined by gravity and time, echoing the early past and hinting at the evolving future. In the deep past, more than 13 billion years ago, the faint beginnings of our galaxy stirred into motion. Clouds of gas, mostly hydrogen and helium from the Big Bang, began to collapse under gravity. These early fragments coalesced into the first clusters of stars, ancient and metal-poor. We call these stars Population 3, and though none survive today, their fingerprints linger in the chemical stories told by their descendants. As the universe matured, gravity continued to build structure. Small proto-galaxies danced through the cosmos, tugging on one another, merging and reshaping. Out of this cosmic ballet, the Milky Way began to grow. Over billions of years, it devoured smaller systems, absorbing their stars, gas, and dark matter. Each merger left traces, star streams that arc through the galactic halo, slow-moving globular clusters, and ripples in the disk. Some of the stars in our sky today were born in other galaxies or in now vanished clouds of the early universe. To uncover this long and complex history, astronomers turn to the stars themselves. Like cosmic archaeologists, they read the signals encoded in stellar light. Two important clues stand out: age and metallicity. A star's age is a direct link to the era it was formed. Metallicity, how rich it is in elements heavier than helium, tells us about its birthplace and when in cosmic history it formed. Early in the universe, there were few metals. The first stars could forge nothing beyond light elements, leaving their successors to build on heavier materials through supernovae. Over time, each generation of stars enriched the interstellar medium. Therefore, older stars tend to have fewer metals, while younger stars often show much more. By studying thousands, even millions of stellar spectra, astronomers can map the chemical evolution of the Milky Way, tracing waves of star formation and merger events across the ages. There is evidence that our galaxy's thick disk formed around 8 to 10 billion years ago, likely kicked up into its puffier shape by a violent merger with another galaxy. This collision would have stirred the stars into higher orbits, changing their paths and injecting energy into the fledgling galactic disk. Later, the thinner disk, rich with gas and still forming stars today, settled into rotation and grew steadily more organized. Sitting quietly outside the galactic plane, in the halo, lies a population of ancient stars and globular clusters. These relics are among the oldest members of our galaxy, some over 12 billion years old. Their sparse metallicity and wide orbits preserve the story of the galaxy's earliest days. Many may have come from dwarf companions torn apart by the pull of the Milky Way's gravity, their remnants now stretched into ghostly streams. The bulge at the galactic center, crowded and enriched, tells its own story. This densely packed region likely formed through early, rapid mergers and violent stellar birth. Over time, stars orbited inward or were driven there through instabilities in the galactic disk, adding to the bulge's mass and complexity. Some theories suggest that the bulge also formed as gas fell toward the galaxy's center, triggering bursts of activity around the supermassive black hole at Sagittarius A star. Even today, the Milky Way is still growing. Several small dwarf galaxies orbit nearby, and some are already being drawn in. The Sagittarius dwarf galaxy, for instance, is caught in an extended process of merging, its stars spilling into looping arcs through the galactic halo. These ongoing interactions continue to shape the structure of the Milky Way. adding to its stellar populations and subtly changing its mass and form. The evolution of the Milky Way is not a closed story. From its primordial collapse to its massive mergers and its future collision with Andromeda, it is part of a vast web of change. Each star records a page of that story. Each orbit, each trace of element, allows us to look deeper into time. Through the stars, we uncover the life story of our galactic home, written in the language of light and motion, unfolding over epochs that stretch across the history of the universe itself. The Milky Way drifts within a quiet corner of the cosmos, nestled in a modest collection of galaxies known as the Local Group. This cluster of more than 50 galaxies is held together by gravity, each system tracing a slow and graceful path through intergalactic space. At its heart, the Local Group is dominated by three major spirals: our own Milky Way, the Andromeda Galaxy, and a smaller but still significant Triangulum Galaxy. The Milky Way and Andromeda are the two giants of the Local Group, nearly matched in mass and size. They are separated by roughly 2.5 million light-years of emptiness, yet they are bound in a dynamic embrace shaped by their mutual gravity. Observations of tiny shifts in their light tell us that Andromeda is heading towards us, not drifting away. Over billions of years, this slow approach will culminate in a cosmic merging that will reshape both galaxies forever. Andromeda may be slightly more massive than the Milky Way, but their structures are strikingly similar. Both possess sweeping spiral arms, spinning disks of stars and gas, and bright, dense cores. Between them lies Triangulum, the third spiral galaxy in the Local Group. Though far smaller, Triangulum plays a role in this ongoing celestial dance. It too may have interacted with Andromeda in the past, and perhaps again in the future it will be drawn into the growing gravitational drama between the two larger galaxies. Together, these three monumental structures form the backbone of the Local Group. The remaining members are a collection of dwarf galaxies, some faint and irregular, many of them satellites orbiting the giants. The Magellanic Clouds, visible from the southern hemisphere, are among these smaller companions. Trailing streams of stars and gas suggest a long history of tidal interaction, a testament to gravitational forces that slowly shape the group over cosmic time. Yet, even the Local Group is but a small part of something far greater. Surrounding us is the Laniakea supercluster, a sprawling collection of galaxy groups and clusters stretching over 500 million light-years across. The word Laniakea means immense heaven in Hawaiian, a name chosen to honor both the vastness and the elegance of this part of the universe. Within this grand landscape, the Local Group resides on one of the outer filaments, like a thread woven into a cosmic tapestry. Laniakea itself is not centered around a single point. Rather, it is defined by flow, by the movements of countless galaxies drawn together by gravity, pulling toward a central region known as the Great Attractor. This immense gravitational anomaly lies hundreds of millions of light-years away, buried behind the dense plane of our own galaxy's stars and dust. Its precise nature is still uncertain, but its effect can be measured. Galaxies move like schools of fish drawn to some distant force beneath the waves. Our galaxy's motion within Laniakea is part of a larger story, the story of cosmic structure. The Milky Way orbits its center, is drawn toward Andromeda, all while the Local Group is swept along streams of gravitational flow within an intricate web of galaxy clusters and voids. This web, collectively called the Cosmic Web, is the largest known structure in the universe, shaped by dark matter and the expansion of space itself. Being here, somewhere in the outer limb of the Milky Way, inside the outskirts of the Local Group, and drifting in a quiet channel of Laniakea, we are part of this improbable journey. All that we call familiar Everything we can see with the most powerful instruments takes place within this vast structure. It brings a sense of context, a reminder that even as we look up at the stars in wonder, we are also moving through an unimaginably vast landscape, carried quietly through the cosmos on a path defined by gravity and time. The Milky Way is not a fixed or isolated entity. Like everything in the cosmos, it is in motion, part of a larger gravitational story unfolding across billions of years. At the heart of this story lies a remarkable future event, the predicted collision and eventual merger with our nearest galactic neighbor, the Andromeda Galaxy. Separated by just over 2 million light-years, the Milky Way and Andromeda are drawing closer together. Though it's hard to imagine, given the vast emptiness between them, observations show that Andromeda is approaching us at a speed of about 110 kilometers per second. This meeting, though called a collision, will not resemble the crashing of solid bodies. Galaxies are made mostly of empty space, scattered with stars so far apart that direct star-to-star impacts will be rare. Instead, as the two giants begin to interact, their shapes will distort. Spiral arms will stretch and twist under gravitational forces. Tidal interactions will fling streams of stars into intergalactic space. Gas clouds will be compressed, triggering intense waves of star formation in both galaxies. The timeline of this future is immense. Current models suggest that the first close approach will occur in about 4 billion years. The galaxies will not collide all at once, but will pass through one another, loop around through gravity, and eventually merge. Over the next 2 billion years after the initial contact, they will complete this cosmic union, settling into a new, larger galaxy. The final galaxy will not look like either the Milky Way or Andromeda. The elegant spirals that define both will vanish. The merge system will take on an elliptical shape, a swollen, smooth profile with older stars dominating its light. Astronomers have even given this future creation a name, Milkomeda, a testament to a universe that is never static, always reshaping and evolving. What will this mean for the solar system? The Sun, currently orbiting the center of the Milky Way at a distance of about 27,000 light-years, is expected to remain intact throughout the merger. While its path may shift due to changing gravitational fields, simulations show that it will likely be carried into a new orbit around the heart of Milkomeda. From Earth, if it still harbors life, the night sky will be transformed. Over generations of time, a vast glowing arc of stars from the encroaching Andromeda Galaxy will spread across the heavens, a breathtaking testament to galactic destiny. In the longer term, the evolution does not end with Milkomeda. Beyond individual galaxies and mergers, the universe itself is expanding. Distant galaxies, not bound by gravity to our local group, are accelerating away due to dark energy. As trillions of years pass, the distant cosmic web will fade from view. Any future observers in Milkomeda may see only the stars of their own galaxy. The wider universe will have receded beyond the limit of observable light. Eventually, star formation will decline. Gas supplies will dwindle. The most massive stars will burn out, and the smaller, longer-lived stars, like red dwarfs, will slowly fade over hundreds of billions of years. Milkomeda will become a quiet galaxy, filled with ancient stars, black holes, white dwarfs, and the dark remnants of a once vibrant stellar population. This is not a story of loss, though. It is the continual unfolding of a grand cosmic cycle. Stars are born and die, galaxies collide and reform, and through all of it, the laws of physics guide and shape the cosmos. Our Milky Way is not forever, but its destiny is written in the stars.